Hi everyone. In previous class we learned electric flux and electric dipole and different cases of electric charge, so electric field due to electric dipole, and physical significance of the electric dipole. So today we will discuss continuous charge distribution. In this topic, so for example, we consider individual charges q1, q2, q3, q4, q5 on a infinite charged wire. Then these individual charges are called the microscopic charges, that is discrete charges. We consider macroscopic charge distribution. Continuous charge distribution is nothing but macroscopic. Macroscopic is nothing but the combined, okay, the system of charge. So we define individual definitions, that is linear charge density, second one surface charge density, third one volume charge density. Okay, here linear charge density, surface charge density, volume charge density. Here first of all we consider linear charge density. Linear charge density. Linear charge density is nothing but the charge is accumulated. Okay, the charge is considered a long conductor per unit length is known as the charge accumulated on a long conductor, per a length, a unit length, that is L, is known as linear charge density, that is linear charge density. Okay, here the conductor length is L, so then charge, individual charge is Q, here Q, the macroscopic charge is Q. Then lambda equals to, lambda is nothing but linear charge density. Linear charge density lambda equals to Q by L. Okay, so L is length of the charged wire, okay, charged conductor. So Q is the charge, macroscopic charge of this conductor, then lambda equals to Q by L. So here units, SI unit for lambda is, so what is lambda here? Linear charge density, so that is coulomb per meter. Second one, surface charge density. Surface charge density. Here surface charge density is nothing but the charge on the surface of the conductor. Okay, here the charge on the surface of the conductor surface of the conductor for a surface is called surface charge density. Surface charge density. So for example, we are consider a cylinder. Okay, so for example, we are consider a plate. So for example, this is a conducting plate. Okay, this is conducting plate. This conducting plate is accumulated positive charges. The macroscopic charge is q here plus q. Okay, then it is consider only length and width. So then length into width equals to here surface, area of the surface. So then here it is denoted with sigma, surface charge density sigma equals to, that is q by s. S is the surface area. Then here SI unit for sigma is coulomb per meter square. Okay, here another one we consider volume. So then volume charge density. Volume charge density. So here volume charge density is nothing but the charge included in the macroscopically small volume delta V that include a charge number of include large number of macroscopic charge constants charge is called volume charge density. The volume charge density is denoted by rho equals to, so charge, macroscopic charge by volume. Okay, here SI unit for rho, that is volume charge density, is coulomb per meter cube. This is volume charge density. So the volume charge density for a sphere, so we consider a sphere, the volume charge density, so here rho equals to q by the volume of the sphere is 4 by 3 pi r cube, like. So this is about the linear charge density, surface charge density, volume charge density of macroscopic charge. So our next topic is Gauss law. The Gauss law is nothing but the total electric flux linked with a closed surface called Gaussian surface is 1 by epsilon naught times the net charge enclosed by the closed surface is called the Gauss law. So this Gauss law is the total electric flux linked with a closed surface. So compulsory. So it is a closed surface, closed a sphere, a cylinder, or a parallelepiped shape, a rectangular shape, like that. The total electric flux linked with a closed surface called, that is a Gaussian surface, is 1 by epsilon naught times of the net charge enclosed by the closed surface. So it is also written as pi equals to the total electric flux equals to, electric flux is nothing but the surface integral of E bar dot ds bar equals to q by epsilon naught. Okay, it is the Gauss law. Alternatively, it is also written as Gauss law can be stated as, okay, that the surface integral of electric field and a closed surface is equals to 1 by epsilon naught times of the net charge enclosed by the closed surface. So it is called the Gauss law. Okay, the Gauss law is derive the equation for the electric field of any closed surface. So here the Gauss law is explained with a so we can derive the Gauss law equation for a closed surface. We consider a closed surface, so it is a sphere. For example, the sphere center is point O here, the point O. The radius of the sphere is r. So we consider here this is a surface, a small surface area. The surface area is, this is electric field. Okay, it is accumulated positive charge here, or negative charge, anyone. So we consider a positive charge. So then the positive charge is considered, then here and the same direction ds bar also is same direction. Okay, now the charge is accumulated, the net charge is q here, the net charge is q. Then the electric flux through an area element ds bar is, okay, this is ds bar, the area element, and the electric flux, that is delta pi equals to, okay, small electric flux, so delta s equals to E bar dot ds bar. Okay, so here it is equation number 1. Now delta pi equals to, so from the equation of the Coulomb's square law, electric field, so then here the electric field equation is q by 4 pi epsilon naught into r square. Okay, what is the distance here? The distance from the center is, from q is r. So r square into r cap dot ds bar. Okay, here this is equation number 2. Here r cap is unit vector. We know that. So it is a unit vector, the radius vector from the center to the area element. So this is the direction of unit vector. Same the direction of the area of the surface, this unit vector. Then here we know that the r cap into ds bar equals to, okay, it is ds bar a vector into unit vector is equals to magnitude. So then delta pi equals to q by 4 pi epsilon naught r square into ds. Okay, this is equation number 3. Since so you can dive so ds bar into r cap equals to the magnitude only ds or delta s, anyone. Now the total electric flux, so it is a part, so here another part, here another part, here another part. The total electric flux is nothing but the summation of, so total electric flux pi equals to sigma, okay, sigma all ds, all delta s into q by 4 pi epsilon naught r square into ds. Okay, here q by 4 pi epsilon naught into r square, this is common. Okay, here pi equals to q by 4 pi epsilon naught r square sigma all ds into ds. Okay, so ds is nothing but the difference of very small part of the area surface area. So all the sigma is nothing but the summation of algebraic summation of the all areas. So then it is equals to the total surface. So then here pi equals to q by 4 pi epsilon naught, here 4 pi epsilon naught r square into total surface of sphere, that is S. Okay, so then pi equals to q by 4 pi epsilon naught r square into total surface of the sphere equals to, what is the formula? 4 pi r square. Okay, here so we can cancel out 4 pi and 4 pi can cancel, r square gets cancelled. So then the remaining part is pi equals to q by epsilon naught. So this is the Gauss law. The Gauss law, the total electric flux linked with a closed surface, this is a closed surface, equals to 1 by epsilon naught times of the net charge enclosed by the surface, closed surface. So pi equals to q by epsilon naught. Next, our next topic is some important points of Gauss law. Some importance of Gauss law. So the Gauss law is explained in a closed surface. The Gauss law is true for any closed surface, that is any shape of the closed surface, no matter that its shape and size. Okay, so it is applicable for small size and big size, and it is also applicable for the different shapes, but it has compulsory symmetry. Second one, the term Q on the right side of the Gauss law. Okay, Q is the charge, net charge. Include the sum of the all charges enclosed by the surface. Okay, all charges, sum of the all charges. For example, Q1, Q2, Q3, Q4, etc. Then the algebraic sum of the charge Q equals to algebraic sum of the all charges enclosed by the surface. The charges may be located anywhere inside the surface. Okay, inside the surface it is anywhere. The algebraic sum equals to the total net charge. So in the right side of this equation. Third one, the Gauss law is help us to calculate the number of electric lines of the force that are radiated outwards from the 1 coulombs of law. So 1 coulombs of charge. So here the Gauss law is helps calculate the number of electric lines. Okay, the number of electric lines, for example, so we are consider the electric lines like here, electric lines. So this is the electric field. So we consider a shape, so like the rectangular shape. So for a rectangular shape, how many electric lines are passed? So 1, 2, 3, 4 through the certain area. So then it is helps us, it is calculate the electric flux. So what is the equation? Q equals to Q by epsilon naught. So then the electric flux, the total electric flux in this area equals to the charge. So it is outward direction of the charge, 1 coulomb of charge. So this is about the number of electric lines of the forces. Fourth one, Gauss law is valid for stationary charges as well as the rapidly moving charges. Okay, it is valid for the electrostatic charges and the current electricity also. Okay, when the charges are moving with rapidly, and it is also applicable for the stationary charges. Stationary charges is nothing but the charge is on a conductor at a stationary motion. Okay, stationary motion is nothing but it is a constant position. Next one, Gauss law gives the relation between the electric field and the charge. Okay, so here the equation is pi equals to circle integration of E bar dot ds bar equals to Q by epsilon naught. Okay, this relation is the relation between, it is also we have taken the relation is circle integration of, okay, the circle integration of E dot ds, E bar dot ds bar equals to Q by epsilon naught. So then the Gauss law gives the relation between E bar and the charge, electric field and the charge. And this Gauss law is often useful towards a much easier calculation of the electrostatic field when the system is symmetry. So compulsory the system is some symmetry. It is useful to derive the equation for the electric field. So from this equation, circle integration of E bar dot ds bar equals to Q by epsilon naught. So for example, we consider a long thin wire, thin conductor. So its charge is positive charge. Then we consider here the symmetry, Gaussian surface is a cylinder. Okay, so in this position the electric field is constant, it is constant, here also constant, here also constant. So it is called the symmetry. So same distance from this minimum mid position. So it is the system has symmetry. So for example, we consider a sphere. So for this conductor, so this is a long infinite conductor. So we consider a Gaussian sphere. Okay, the distance is more here. the distance is less. So then the electric field is inversely proportional to r square. When at this position the electric field is less, in this position electric field is more. It is not symmetry. So the Gauss law is often useful towards a much easier calculation to the electrostatic field. Okay, the electrostatic field. So when the system has symmetric Gaussian surface compulsory, we consider the Gaussian surface for individual electric conductor has symmetry. These are the some importance of the Gauss law.